So today is the eighth lecture of our prerequisites of knowledge of sequences for sequences, and today will be the last class. So we have come a long way in this one. So today will be the last class on this thing. So yesterday we finished at the this thing, seeing that this sequence 1 plus half plus this one is not a Cauchy sequence. And I promised you that I'll show you some graphical representation of Cauchy criteria, which was half baked yesterday. So today it is ready. Now, so this is this is x and y axis, n axis, natural number axis, and the sequence axis. This one, okay. Here over here we'll be putting the sequence values, and over here we'll be putting the n's. So this is my epsilon band. Cauchy sequences, that means they close infinitesimally close to each other. So this is my one choice of epsilon band. Now here the sequence is coming, going inside that band. Now from here, from this n equal to k, after this n equal to k threshold, everything is inside this band. Every term has their mutual distance less than epsilon. This is my epsilon band, and everything is going inside this epsilon band. So that is what is meant in the Cauchy sequence. The individual terms are getting close enough to each other. The mutual distances of the terms are getting close, as small as we want. This is what Cauchy sequence means. This is what the description of Cauchy sequence is. This is what happens. The terms get arbitrarily close to each other over here. Now the thing is, it does not talk about the limit. I do not know whether this point with this value will be the limit, or this value will be the limit, or this value will be the limit. I do not know which value will be the limit. Okay, Cauchy sequence does not talk about the limit. It only talks about the convergence. It talks about it in case of real sequences, in case of sequences of real numbers, Cauchy sequence guarantees the convergence of real sequences. Okay, in case of other numbers, in case of rational number, this does not guarantee convergence. Just like, understand this thing, Cauchy sequence does not have to do anything with the limit. So suppose this is a sequence of rational numbers, and assume that they are converging to this number, to say this number. Okay, suppose they are trying to converge to this number. Now what is happening is that this number, we do not know whether it is a rational number or not. If this is not a rational number, then this line doesn't exist here in Q. In the set of rational numbers, this set line is not there. So the terms are getting actually infinitesimally close to each other, but not getting anything to gather around. So it is like you have got a collection of iron ore which are very much accumulated to each other, but there is no magnet inside. If there is some magnet, then they will be attached to that. They will be stick to that magnet. But over here in Cauchy sequence, in case of incomplete spaces, the iron ores are actually sticking to each other, but there is no magnet inside. Had there been a magnet, it will definitely be a Cauchy sequence. Okay, a convergent sequence is always Cauchy. Be it rational sequence of rational numbers, or sequence of real numbers, or sequence of complex numbers, whatever. A convergent sequence is always Cauchy. It is only the other part which is of some importance. Importance means which is non-trivial in nature. Okay, so this is what graphical representation of Cauchy sequence is. Okay, we are done with this. Next, equivalence of Cauchy criterion and convergence. Um, a Cauchy sequence of real numbers is convergent. Proof: let xn be a real Cauchy sequence of real numbers. We follow the following steps to show xn is convergent. Now, this one is a very intricate proof. Please pay full attention to this one. You please tell me if your screen gets blurred or anything. My voice breaks. You cannot hear. Please stop me there. You need to understand this on the in the live class. You can always go back for revision, but I'll try to understand in the this thing in the live class. This is important and extremely delicate. Delicate in the sense in the notational sense. The concept wise, it is not that stuff at all. Step one. So we'll follow the steps. Now, first step is we will show that if a sequence is a Cauchy sequence, it has to be bounded sequence. That is what we are going to show. So choose epsilon is equal to 1. Okay, so definition of Cauchy sequence is, if you remember, for all epsilon positive there exists a this thing. Let me go back. Yeah, for all epsilon positive there exists a threshold integer k such that for mn greater than equal to k, distance between xm and xn will be less than epsilon. So that is the definition. Now here choose epsilon equal to 1. Then for that choice of epsilon, you will get a threshold mark integer k1 such that for all mn greater than or equal to k1, distance between xm and xn is less than 1. That is, in particular, choose m to be k1. So we need both m and n to be anything greater than or equal to k1. So there you choose m to be equal to k1. Therefore, this will be xk1 minus xn. So that is xn minus xk1 since modulus is there. So xn minus xk1 will be satisfied for any choice of n greater than k1. So I am fixing n at k1 and letting n vary from k1. So for all n greater than k1, the distance between xn and xk1 is less than 1. So if you break this out, then it will be xk1 minus 1 less than xn less than xk1 plus 1. Okay, so choose b is equal to minimum. Okay, let's go back over here. Yes. So now, okay. Then let me do this thing here. Okay, so here this is what I need. Understand this thing, that suppose I have chosen this epsilon to be 1. Okay, that this epsilon is 1 here. I can go back here. Epsilon to be 1. So then this is my n equal to k1. This is my k1. Let's say this point is my k1. So therefore, what I'm trying to say is this: all the terms after to the right of this, all of them are within one distance from this k1, from this xk1. So they are in this range. That xk1 minus 1 to xk1 plus 1. They are within this range. Okay. Now, so we have tamed the entire tail of the sequence. We have tamed them, the entire tail of the sequence. What remains to tame are the first finitely many terms before this stage happens. So the first finitely many first k1 minus 1 many terms are there. So this is my k1 terms. From here, the tail starts. The tail is tamed properly, and we have got only k1 minus 1 many terms left at the beginning. So these terms we need to take. And so we have got some bound over here. So what do we need to do to bound all these things? So bound of this part, the first part. So this is my upper bound, this is my lower bound for the first finitely many part, and I will compare this upper bound to the upper bound of this one. I will compare this lower bound to the lower bound of this one. So that is what is written over here. Choose b is equal to minimum of first k1 minus 1 many terms, and then the lower bound of this one, lower bound of the tail. Okay, and capital B as the maximum of the first k1 minus 1 many terms, and then upper bound of this tail. So then this small b and capital B will be a bound for everything, for all number n, all index n. The sequence xn will be between small b and capital B. Okay, so that is that shows that it is between the sequence is bounded. So we have, in the first step, this has got 3 steps. In the first step, we prove that a Cauchy sequence is always bounded. Second step, you can always guess, obviously guess that we have a bounded sequence, so a convergence subsequence. We have Bolzano-Weierstrass, we have convergence subsequence. So since xn is bounded by Bolzano-Weierstrass theorem, there exists a convergence subsequence. xnk, let's say xnk of xn converging to x, say. Okay, so Bolzano-Weierstrass says it is a convergence subsequence. Now let us name that. We are naming that xnk. This is the convergence subsequence, and that is converging to the real number x. Fine. Therefore, apply the definition of convergence. Therefore, for epsilon positive chosen arbitrarily. So see, this epsilon is chosen arbitrarily. This epsilon was chosen as particular one, and that proves that this is bounded. Here we are choosing the arbitrary epsilon at this second step. The first step, epsilon is not arbitrary epsilon. In the second step, we are choosing this epsilon, and this epsilon will be valid till the end of the proof. Okay, this is our arbitrarily chosen epsilon. So therefore, for arbitrarily chosen epsilon positive, there exists k2 such that this one will happen. xnk will be close to x. So for all k greater than k2, understand the sequence is on k here. The subsequence is running on k here. So for all k greater than k2, the absolute value, the distance between xnk and x is less than epsilon by 2. Understand that the intricacies of this proof, that actually is mostly due to the notation, the indices over here. Okay, so follow these indices properly. So here we have changed from n to k. xnk is a subsequence of xn. So there exists a k2 such that for all k greater than k2, k is the running index here. xnk minus x is less than epsilon by 2. Okay. Now let us see this one first. Step 3. So in the Bolzano-Weierstrass says that so in the step 1 we proved a Cauchy sequence is bounded. In step 2, Bolzano-Weierstrass says bounded means convergent subsequence. So that convergent subsequence, we have the limit of that convergent subsequence, and that limit will be the limit of the sequence. So Cauchy is to show something is convergent in the traditional sense, in the definition of convergence, we need to produce a limit. How do we find that limit? In this way. So we first prove this is bounded. As soon as we get bounded, Bolzano-Weierstrass will say bounded means there is a convergence subsequence. Now there is convergence subsequence, convergence is there, so that means we have got a limit there. Then the Cauchiness of the sequence will drag the entire sequence to that limit. I will show that thing in graphically over here. This is clumsy at the first look. I will show with the animation. Now understand these things over here a little bit, then it will be easy to understand the graph. That the cochiness of the sequence drags the entire sequence to converge to that point where the subsequence is converging to. So understand this thing. Forget about these ones over here. So since it is Kochi, the terms are getting close to each other. So therefore, I mean, what is happening is there is a part of the sequence. There is this part of the sequence which is converging to a limit, and since the other part is glued to this one by Cochiness, since they are close to each other, these two parts are close to each other. The other part is also getting close to this point as well, this limit as well. Okay, so that is the thing. So since it is Kochi, it will be close to each other, and that is my K3. After K3, the Kochiness kicks in. After K3, the Kochiness kicks in, and then the each term after that is close to each other, close to X. Now let's see the animation. Okay, so this is my axis. So this is my sequence. Okay, there is no animation for the sequence here. So this is my sequence. So what is that? What is this? This is one part of the sequence. This is another part of the sequence. Okay, this is a subsequence. This is a subsequence. Now, so as we this is the last example only. So this is x1. This is x2. This is x3, x4, x5, x6, x7, x8, x9, and so on. This is So this is my sequence. Okay, so they are this is one subsequence. Say this is the even subsequence, and this is the odd subsequence. But they are subsequences anyway. So okay, so we assume that this part of the sequence, so this subsequence is a convergent one and converges to this point X. Okay, so this green part, this green subsequence is a convergent subsequence and converges to this point X. Fine. These are the epsilon bounds around x minus epsilon to x plus epsilon. Okay. Then these are epsilon by 2 bounds around x. So x minus epsilon by 2, x plus epsilon by 2. So this green subsequence converges to x, so it goes within the epsilon by 2 neighborhood around x after k equal to k2. Okay, after k equal to k2, they go inside the epsilon by 2 bound near x. So that is exactly what we have here. By the Bolzano-Weierstrass, we have seen that there exists a K2 such that after K2, xnk minus x is less than epsilon by 2. Exactly that is happening here. This is K equal to K2. So this is N1, N2, N3, N4, N5. Because as I told you, this is even one and this is the odd one, whatever, the other way around. So they are not consecutive lines and they are not consecutive points. Consecutive points are this one and this one, then this one, then this one. So they are alternatively consecutive lines are basically alternating colors. So of the same color, the green color is not consecutive line. So consecutive point. So this is my N1, this is my N2, this is my N3, N4, N5, N6, N7, and so on. So this is my NK2. So after, so this is my NK2 is close to epsilon by 2 close to x. NK2 plus 1, it is epsilon by 2 close to l. NK2 plus 2, that is epsilon by 2 close to x, and so on. So that is, this characterization is for the Bolzano-Weierstrass one. So this is there exists a natural number k2 such that for all k greater than or equal to k2, this is for the Bolzano-Weierstrass. Now let's come to the Cochiness. So this one is my epsilon by 2 band. This band is for my Cauchiness. This epsilon by 2 band I am considering over here. Okay, this blue one. Okay, this blue band over here is my epsilon by 2 band. This one kicks in after this stage. After this stage. So after this stage, you see all the pink dots and the green dots, they are close to each other. All the pink dots and the green dots, they are close to each other. They are epsilon by 2 close to each other. Then what happens if you choose something over here? If you choose any point over here, then this is your point. Or say this is your point. This point you want to measure the distance from this x, from this orange line x. This is your point, point x. So the distance of this point from x is guaranteed by this way. This is less than distance of this pink point from this pink point, and this green point. Pink point and this green point. The distance between pink point and this green point, that is less than epsilon by 2, and this green point and this green point and the this green point and the x. So that is also less than epsilon by 2. So the total distance of this one, this pink point and x, is actually smaller than epsilon by 2 plus epsilon by 2, that is smaller than epsilon. So that lies within this epsilon band. So step 3, since xn is Cauchy for the chosen epsilon positive, there exists a K3 such that for all mn greater than equal to K3, xn minus xn is less than epsilon by 2. Less than epsilon by 2. Now, so this is from the Cauchiness. So call K naught is equals to maximum of K2 and K3. Okay. So I want both Bolzano-Wurster's, the convergence of the subsequence to happen, and Cauchiness also needs to happen. So K naught is equals to K2 minus maximum of K2 and K3. So that is over here. So nk naught is that, this is my K3, this is my nk3, this is my nk naught, this is my k naught. So k naught is equals to maximum of K2 and K3. Then nk naught is greater than or equal to k naught. This is from the definition of subsequence, that the index sequence is a strictly increasing sequence. So nk naught must be greater than k naught, greater than or equal to k naught. K naught is greater than or equal to K3 just by this, since it is maximum, and hence for each n greater than k naught, choosing m equal to nk naught, we see that xn minus xnk naught is less than epsilon by 2 from here. So I need both m and n to be greater than or equal to K3 in order to this inequality to happen. So I am choosing m to be nk naught. Nk naught is definitely greater than or equal to K3, so that works, and n is anything greater than equal to k naught. So for n greater than or equal to k naught and m equal to nk naught, xn minus xnk naught is the distance between them is less than epsilon by 2. Also, k naught is greater than or equal to K2. So Bolzano-Wurster's is there, still there. So by star xnk naught, Bolzano-Wurster's, let's go back over here. So k naught is greater than K2. So for k greater than k naught, xnk minus x will be epsilon less than epsilon by 2. So in particular, if you choose xnk naught, then xnk naught minus x will also be less than epsilon by 2. So therefore by star xnk naught minus x is less than epsilon by 2. So we are done now. Therefore for all n greater than or equal to k naught, xn minus x is less than, triangle inequality simple, insert xnk naught, xn minus xnk naught plus xnk naught minus x. This is less than epsilon by 2, this is less than epsilon by 2, so total is epsilon. Since epsilon is arbitrary, xn is convergent. This finishes the chapter, prerequisite chapter on sequences.